Hi everyone, welcome to another chapter of physics in the Easy Board's NCERT Simplified series. Today we are going to discuss the chapter Magnetic Effects of Current. So in the previous chapter of physics we have discussed about the basics of electric current as well as electricity. So today we are going to study another effect of current which is known as the magnetic effect of current. In this chapter, we will deal with the basics of magnetism, magnetic field lines, production of magnetic field due to current that is flowing through the circuit, about the concept of electromagnetic induction, basics of alternating current, and the applications of induced current as well as alternating current. So let's get started. As you can see, the number of slides is very less because it's a very small chapter. There is no numericals based on this chapter. Questions can be little bit higher order thinking skills questions, as well as it can be little bit application level questions, but the chapter is very simple. So let's get started with this chapter. First topic that we are going to discuss here is magnetic field and magnetic field lines. So what do you mean by magnetic field? In the previous chapter we have studied about electric field. What was electric field? It is a region in space where the effect of a charge can be felt. That is known as electric field. That means if you are standing in electric field, you can feel that some charge is here nearby, right? So if you are alone in a room and if a spider is there, then what will happen? You will have some sort of a fear, right? That the spider is here somewhere. So this is a field that is having spider around. Similarly, this is a region in space where you have a feel that a charge is somewhere near. That is known as electric field. Similarly, magnetic field is a region where the force of a magnet can be felt. That means if you are experiencing a magnetic field in some region, that means you can make sure that a magnet is nearby. That is the meaning of magnetic field. So if you have to represent a magnetic field, then you can do that by drawing magnetic field lines. Now how can you draw magnetic field lines? That we are going to discuss shortly. So like the previous chapter, we have studied that like charges repel each other, unlike charges attract each other. So the same way, like poles repel each other and unlike poles attract each other. That means north pole and north pole of two magnets, they will repel each other, whereas north pole of one magnet attracts with the south pole of another magnet and vice versa. So now let us draw the magnetic field lines due to a bar magnet. For that, first we will draw the bar magnet. This is the bar magnet. Now what we have to do, always remember that the magnetic field lines starts from the north pole and it will move towards the south pole. And inside the magnet, it will move from the south pole to the north pole. Please check this diagram very carefully. So here you can see that outside the magnet, you can see that it is moving from the north pole all the way to the south pole. But inside the magnet, you can see that the magnetic field lines are moving from the south pole to the north pole. That means it is now forming a complete closed loop over here. So this is how you are going to represent the magnetic field lines. You will start from the north pole and then starts running towards the south pole. Now you don't have to go back to the north pole to the external of the magnet, but you can move to the internal of the magnet in the opposite direction, that is from the south pole to the north pole. So this is how you are making a loop for direction of the magnetic field. Now talking about the direction of the magnetic field, it is taken to be the direction in which the north pole of the compass needle moves inside it. So we can say that the direction of magnetic field is in the north-south direction, and inside the bar magnet the field lines move in the south-north direction, and hence we can say that the magnetic field lines are closed curves. Now how do we define the strength of a magnetic field? How do we define the strength of a spider? If we are moving close to the spider, then we can say that the spider is mighty, right? Similarly, the proximity of the lines represents the strength of the magnetic fields. So if more number of fields are around the magnet, we can say that in that particular region the strength of the magnetic field is very high, but if it is away from the magnet, then its strength is going to be very less. And also you can observe one thing, that no two field lines cross each other. What is the reason for that? How can a compass needle deflect to two different directions at the same time? It's not possible, right? So due to the same reason, we can say that no two field lines are found to cross each other. Next, we're going to study different topics now, but we don't have to go to the equations or derivations. Equations and derivations of all these topics we'll be discussing in class 12th. So now let's start with the first topic here, that is magnetic field due to a straight current carrying wire. So I have a straight current carrying wire over here. So I'm going to find out what is the magnetic field that is generated due to this straight current carrying wire. So what I should do is I have to connect this wire to a circuit. That means through a cell, through a switch, everything we are going to connect. Now as you know that the cell provides potential difference and that generates current. So now what happens is that this current can move in either clockwise direction or in anti-clockwise direction. So look at the first picture. Here what can you see? Here you can see that current always flows from the positive terminal to the negative terminal. That means this is moving, this is the direction of current, right? Since the current is moving in this particular direction, this is anti-clockwise or clockwise direction. This is the clockwise direction, right? The clock also moves in the same manner. Whereas in this case you can see, in the second case you can see that this is the positive terminal and this is the negative terminal. So the current is flowing in the anti-clockwise direction. So let us understand what will happen if the current flows in clockwise direction and what will happen if the current moves in anti-clockwise direction. If the current is moving in the clockwise direction, then the compass needle will show deflection towards the south, or the north pole of the magnet will move towards the current carrying loop. That means if the current is moving in the clockwise direction, then the compass will show deflection towards the south pole. It will show deflection towards the south end of the magnetic needle. So that is why I have represented this symbol over here. Now this is a very easy trick to study the direction. If the current is flowing in the clockwise direction, then you can draw a symbol for clockwise direction. Clockwise direction is you're starting from 12, you're moving like this, right? So this is the clockwise direction. It is moving like this. This is clockwise direction and this is again moving in the clockwise direction. So this is S is a symbol for clockwise direction, and if you write N, this is the anti-clockwise direction. So this is the representation of clockwise and anti-clockwise direction in magnetic physics. So if the current is flowing in the anti-clockwise direction, then we can say that the magnetic needle is deflecting towards the north side, or we can say that the south pole of the magnet is moving towards the current carrying loop. That means, what is the meaning of that? Here if it is showing deflection towards the south side, that means now this loop is going to act as the north pole of the magnet. Always remember that. If current is flowing through in the clockwise direction, then that particular loop is going to act like the north pole of the magnet. That is why the compass needle is deflecting towards the south side. Whereas if current is flowing in the anti-clockwise direction, now this particular loop is going to act as the south pole. That is why the north pole of the magnet is attracting towards it, or the deflection is showing towards the north side. Now let us move on to the next part, that is magnetic field due to a straight conductor. So now we just studied magnetic field due to a straight current carrying wire. Now we are going to take a straight conductor and let us see what are the factors on which the magnetic field affects. Magnetic field due to a straight conductor affects on two things. Number one is the strength of current that is flowing through the circuit, and number two is the length. These are the two factors, length of the conductor. These are the two factors which affects the magnetic field due to a straight conductor. So when the amount of current is increased in the circuit, then we can see that the deflection in the compass needle also increases. Hence we can say that the magnitude of current increases and the magnetic field produced decreases, and vice versa. So when length increases, what happens, or the distance increases, what happens, the magnetic field will decreases. So this is the relation which you can conclude from here, that the magnetic field is directly proportional to the strength of the current and it is inversely proportional to the length and also the distance from the conductor. That means if a conductor is placed over here, if you have to find the magnetic field at this point, that is P, and this point, that is Q, you can say that the magnetic field at point P is going to be greater as compared to the point Q, because Q is farther away. So if it is farther away, then what happens? The magnetic field will obviously decreases. Next is the right hand thumb rule that is used to find the direction of the magnetic field which is associated with the current carrying conductor. So here what you are going to do, suppose I have a conductor like this. Now what am I going to do is I'm going to take my right hand and I'm going to curl it like this. Now the thumb is going to show the direction of current and the curled fingers are going to show the magnetic field. So now you can see that the fingers are curled in the inward direction, then the current is in the upward direction. So this is how we are finding the direction. So if the current carrying conductor is like this, then the magnetic field is like this, that is pointing towards me, curling inwards, then the current is towards the right side. So this is how we are predicting the direction of the magnetic field, direction of the current. Suppose this is the conductor and now I am going to say that the current is flowing towards the left. That means I am going to point the thumb towards the left. Now you can see that these fingers are curling inwards again, and this is going to be the direction of magnetic field, that is from here to here. This is the direction of magnetic field because the thumb is pointing towards this direction and now the fingers are curling again inwards. So that is the direction of magnetic field. So this is how you predict the direction of magnetic field using the right hand thumb rule. That is, thumb always will give us the direction of current and the curled fingers will give us the direction of the magnetic field. Next is the magnetic field due to a current carrying circular loop. So again, this you have a detailed derivation in class 12th, but just now we have to study that the magnetic field, it is always denoted by the letter B, that is directly proportional to the current, it is directly proportional to the number of loops which are present, and it is inversely proportional to the distance. So they can ask, if the distance is increased, what will happen to the magnetic field? It will decrease. If the current that is flowing through a circular loop increases, what will happen to the magnetic field? It will increases. If the number of loops increases, what will happen to the magnetic field? Again, it will increases. And also this diagram is important. This field diagram, field line representation of a circular loop is important. Now let us talk about the magnetic field due to a current in a solenoid. Now what is a solenoid? Solenoid is just like a spring. It is a coil of many circular turns of insulated copper wire which is wrapped closely in the shape of a cylinder. That means I am taking some copper wires, and insulated copper wires are taken, and that is curled like this, like a spring. So that is known as a solenoid. Now what happens is that the magnetic field is same at all points inside the solenoids. If I take a point over here or over here or over here, the magnetic field is going to be same inside every single point or inside the solenoid. A strong magnetic field produced inside a solenoid can be used to magnetize a piece of magnetic material like soft iron when placed inside the coil. That means the magnetic field is same inside every point of the solenoid. So if I am inserting some soft iron or something, then if I am connecting it to a circuit, what happens is this particular soft iron is subjected to the same magnetic field for a longer duration. So it will get magnetized because it is a magnetic material, and after it gets magnetized, it can be used as a permanent magnet. This process is known as electromagnetic effect, also known as, this is the method of preparation of an electromagnet. So for the preparation of electromagnet, you take a soft iron core and you are going to insert it inside a solenoid, connect it to a circuit and close the circuit. Now what happens is, when the current flows through the circuit, there is formation of magnetic field, and that constant magnetic field will magnetizes the soft iron core, and now switch off the circuit, you can take out the iron core, that is going to act as a permanent magnet. So this is known as electromagnet, which is formed by passing electricity on a solenoid. So this is important point that is related to electromagnet. 1 to 2 mark questions can be asked based on electromagnet, and also questions can be asked regarding what is the magnetic field at each and every point inside the solenoid. Even that can be asked for the exam. Now we are going to find the force on a current carrying conductor in a magnetic field. We have seen what is the condition of field that is inside a current that is due to a current carrying conductor. Now let us study what is the force due to a current carrying conductor. An electric current flowing through the conductor, it will always produces a magnetic field, and this field will exert a force on the magnet which is placed in the vicinity of the conductor. That means if I have a conductor like this, there will be some magnetic field that is produced due to this particular conductor, and now if I am placing a magnet in the vicinity of that field, then it will experience as a force. Now a scientist known as Ampere, he suggested that a magnet must also exert an equal and opposite force on the current carrying conductor. So the direction of the force can be reversed when the direction of the current or magnetic field is reversed. What is the meaning? Ampere is just suggesting an implication of the Newton's third law of motion. That means if this conductor is exerting some force due to the magnetic field around it, then the magnet is also exerting a force which is equal and opposite to the force that is exerted by the conductor. And another thing is, the direction of the force can be reversed if the direction of the current or direction of the magnetic field is reversed. This is another observation that was made by Ampere. And the magnitude of the force is highest when the current is at right angles with the direction of magnetic field. That is another important point. If the direction of magnetic field and current is in perpendicular direction, then the force is maximum. That means if current is in this direction and this magnetic field is in this direction, then the force will be maximum. That will be perpendicular to both of these, and that will be maximum. And if you have to study the equation, you can study the equation also. It is F is equal to B I L sine theta. This is the equation for force due to a current carrying conductor, BIL sine theta. So sine theta is maximum when theta is equal to 90 degree. That is why the force is maximum when theta is equal to 90 degree, and theta is the angle between B and I. This is B and this is I, and theta is the angle between B and I. Then force is given by BIL sine theta, and when sine theta is maximum, force is maximum. Sine theta is maximum when theta is equal to 90 degree, so F is maximum when theta is equal to 90 degree. That means B and I are perpendicular to each other. Now if you have to find the direction of the force, that is given by the Fleming's left hand rule. So to predict Fleming's left hand rule, you need to keep your left hand in such a way that you have to take these three fingers. This is the thumb, this is the forefinger, and this is the middle finger. Now what you have to do is you have to arrange them in a mutually perpendicular direction. This is the meaning of mutually perpendicular direction. So you have to hold these fingers in a mutually perpendicular direction. Now the thumb is going to show the direction of the charge. Forefinger is going to represent the field, and the middle finger is going to represent the current. So you have to practice multiple times, then it will be very easy. Forefinger is going to represent the field, current is going to be represented by the middle finger, and thumb is going to be the motion. So always move your thumb. So thumb is going to represent the motion. Next, forefinger is going to represent the field, F and F. So it is very easy. And middle finger is going to be the direction of current. Suppose the current is moving in the left direction and the forefinger is going in this particular direction. The field is going in this particular direction, that is from south to north direction. Then what is the motion? What is the direction of motion of the charge? That is going to be in the upward direction. If the charge is moving towards the left side and it is given that the field is acting from south to north, then what is the direction of current? The current will be moving in the downward direction. So this is how you are finding the direction of force. So the direction of motion will be same as direction of force. Please take a note of that. Next we are going to study about electromagnetic induction. Now what is electromagnetic induction? So far we have seen that when current is flowing through a conductor, there is a field which is produced around it. A magnetic field is produced around this particular conductor. Now the opposite of this, that is, when the magnetic field associated with the coil changes, then current is induced in the circuit. Now we study that current produces magnetism. Now the reverse we are going to study, magnetism produces current. That means suppose we had an area and in that area we had a particular magnetic field. if we are changing the magnetic field of this particular coin, if we are changing it by some extent, then what happens is that the current is induced in the circuit because of this change in magnetic field, and this phenomenon is known as electromagnetic induction. Now we can see the current in a circuit, whether current is flowing in a circuit or not, by using a galvanometer. Now you may ask me, what is the use of ammeter then? Ammeter can be used to find the magnitude of current which is flowing in the circuit, and galvanometer is used to detect, this word is important, detect the presence of current. That means if current is flowing through the circuit, the galvanometer will show deflection towards the right or left depending on the direction of current. So if it is standing at 0 mark only, that means no current is flowing through the circuit. So galvanometer is a device which is used to detect the presence of current that is flowing through the circuit. It shows deflection according to the direction of current. And we also studied what is electromagnetic induction. When the magnetic field associated with the coil changes, then a current is induced in the circuit, and this phenomenon is known as electromagnetic induction. And the current that is produced due to electromagnetic induction or by changing of the magnetic field of a coil is called as induced current, and the potential difference that is developed is known as induced voltage. It is known as induced voltage. And now if you have to find the direction of the induced current, that you can do by using Fleming's right hand rule. So we have studied 3 rules so far. First one was the right hand screw rule. What is the purpose of that? If current is flowing, then this is the direction of magnetic field. Next we studied Fleming's left hand rule. This is the left hand rule. Thumb is representing motion or force, field is by the forefinger, and middle finger is representing the current. Now we are going to take the right hand. Here thumb is going to be in the motion of the conductor and forefinger is going to be again in the field. There is no change for that. But middle finger, there it was representing the current, but now this is going to represent the induced current. So if these two are known, then easily we can find out what is the direction of induced current. So it's a very easy trick to study the direction of induced current. For that we are using the right hand rule. Now moving on to the next topic, that is alternating current. What is alternating current? You might have heard this word AC, right? What is this AC? In our home, the current that is coming, that is a fluctuating current. It is not a normal current. If steady current is flowing through the circuit, it is difficult for laying such power stations, and transmission of DC is very difficult. Direct current is very difficult. So for that, we are using a current which is known as alternating current, whose direction periodically changes with respect to time. So current whose direction changes periodically with respect to time is called as alternating current, and it is used for domestic purposes. So it is flowing in the form of a wave, and every wave have a frequency. So the frequency of the AC wave is 50 Hz, and the voltage associated with the AC is 220 volt. That is the household voltage that we are getting. Now moving on to the last topic of this chapter, that is DC generator. Now DC generator works on the principle of electromagnetic induction. That means when the magnetic field which is associated with the coil changes, there is a induced current produced, and this induced current can be used for other applications. That is the use of a DC generator. So this DC generator is used to produce the induced current in only one direction, or unidirectional current only, or it is used to produce a DC. And this is how its setup is. We have a magnet. North pole is placed over here, south pole is placed over here. We are placing a loop in between these two. So when we are changing the magnitude of the magnetic field, some current will be induced and that will flow through the circuit. So that current can be obtained by connecting some output source over here. So that is how we are taking the current from the DC generator. So with this we come to a conclusion of this chapter, where we discussed about magnetic field lines, magnetic field due to a current carrying conductor, due to a circular loop, due to a solenoid, and then we discussed about electromagnetic induction, galvanometer, DC generator and AC. So I hope this lecture was useful for you. It was a quick lecture where we completed the entire chapter. So if this was useful, please do like, share, subscribe to the channel so that you does not miss out any important notifications, and please do not hesitate to ask all your doubts in the comment section, as well as join the Telegram channel so that you can communicate with me directly. So Thanks for watching and see you again in the next lecture. Till then, goodbye and happy learning.